Hello, and welcome to part 3 of this video playlist about the preparation of alkylarenes. In this video, we'll have a look at the alkylation of unsubstituted arenes with alcohols, aldehydes, and ketones. Because these starting materials are stable and readily available, these reactions are important for the industrial manufacture of many intermediates, for instance, monomers for the production of polymers. One problem is that water is always formed as a byproduct. Some of the catalysts suitable for alkylations with alkyl halides or olefins are deactivated by water and cannot be used for alkylations with alcohols unless added in large quantities. The specific examples are organized as sketched here. I'll start with alcohols, going from primary to secondary to tertiary to allylic and finally to benzylic alcohols. Then we'll see some examples of alkylations with aldehydes and ketones, including acetals. Within each type of electrophile, we'll start with the alkylation of neutral arenes, then of phenols and anilines, of heteroarenes, and of metallated arenes, including transition metal chelates. As discussed in the previous video of this playlist, strong acids can also bring about the abstraction of hydride and thus oxidation reactions. Therefore, aldehydes or ketones are sometimes formed in Friedel-Crafts alkylations with alcohols, what can lead to diaryl alkanes or styrenes as byproducts. That is why these reactions should be stopped as soon as the starting materials are consumed. At the end of this video, I'll show you some further typical side reactions. Let's start with the specific examples. With alkylations by primary alcohols, these are the most unreactive under acidic conditions because primary carbocations are not well stabilized and tend to rearrange to secondary cations. Here, an excess of paraxylene was alkylated with phenethyl alcohol and 10% of triflic acid. Surprisingly, no styrene or polystyrene were formed. This was because the acid-mediated elimination of water from phenethyl alcohol yielded a relatively stable spirobicyclic cation. Moreover, the large excess of xylene and the dilution with a solvent further prevented polymerization of this cation. This here is an optimized process for preparing dimethyltetraline by acid-catalyzed cyclization of a primary alcohol. One potential side reaction was hydride shift to a secondary carbocation and formation of an indane, but this did not happen. The only major side reaction was dehydrogenation to dimethylnaphthalene.
In the previous two examples, the arenes were electron-rich and easy to alkylate. Electron-deficient arenes, however, are resistant to Friedel-Crafts alkylation or acylation. Here, benzophenone was heated with an excess of propanol and sulfuric acid for 12 hours. A secondary carbocation was formed by hydride migration to the initially formed primary carbocation, but the yield of isopropyl benzophenones was only 26%.
With methanol, or tert butanol, no alkylation occurred, not even after 3 days at 160 degrees Celsius. With methanol, the stationary concentration of methyl cations was probably too low, while the tert butyl cation was too stable and unreactive. Benzene is less reactive than toluene or xylene, but more reactive than benzophenone. With 10% of triflic acid as catalyst, benzene was cleanly alkylated with cyclohexanol. The cyclohexyl cation often contracts to a tertiary methyl cyclopentyl cation, but this cation is less reactive, and its reaction with benzene was not observed here. Here, a secondary alcohol was cyclized to a 7-membered ring. 7-membered rings are formed slowly, and to suppress oligomerization, the reaction was conducted at a low concentration. The type and quantity of catalyst also had to be chosen carefully because di- or trialkyl arenes readily rearrange under acidic conditions. Here, a mixture of iron trichloride and silver hexafluoroantimonate was used. Dichloroethane was a suitable solvent in this instance, but cannot be used with stronger Lewis acids, for instance aluminum chloride, because these also catalyze chloride abstraction from and alkylations with dichloroethane.
Although 5-membered rings are formed more quickly than 6-membered rings, here the acid-catalyzed cyclization of a 3-aryl propanol did not yield an indane but a tetralene instead. Thus, the benzylic carbocation was more reactive and cyclized faster than the initially formed tertiary carbocation. Depending on the substituents, allylic carbocations can be similarly stable and unreactive as benzylic carbocations. Here, benzene was alkylated with an allylic alcohol containing a cyano group and a ketene dithioacetal. Thus, acylation by the ketene or the cyano group were potential side reactions, but a fair yield of allylated benzene could still be isolated. Unsymmetric allylic carbocations can yield 2 different products, and it is far from easy to predict the regioselectivity correctly. In this example, benzene was allylated with complete allylic inversion. With the more electron-rich trimethylbenzene, however, the initially formed Alkylarene cyclized to an indane. Now some examples of alkylations with benzylic alcohols. Benzylic carbocations are often well stabilized and thus unreactive, but selective. Here, anisole was alkylated with a hydroxymethylthiazole and an excess of methane sulfonic acid. The free amino group remained unchanged because the excess of acid kept it protonated during the reaction. Also, thioanisole can be benzylated with high regioselectivity at position 4. Here, the amino group in the benzylic alcohol slowed down carbocation formation due to electrostatic repulsion between the 2 cationic sites. The benzyl oxy group, on the other hand, stabilized the carbocation. This here is an example of the intramolecular benzylation of a benzene sulfonamide. The sulfonyl group is deactivating and metadirecting, but in triflic acid and at low temperature, orthobenzylation occurred nevertheless. I'll show you now some examples of the alkylation of phenols and anilines. Phenols are nucleophilic and easy to alkylate, sometimes by intermediate and reversible formation of an aryl ether. As already mentioned, acid-catalyzed alkylations with primary alcohols tend to yield branched alkylarenes. Some transition metal chelates, however, can react with primary alcohols to yield linear alkylarenes, as in this example. Here, a ruthenium chelate was formed from the phenol and a ruthenium 0 catalyst. Here, a phenol was alkylated in high yield with a tertiary carbocation. Again, a clean orthoalkylation occurred. Because alkylations with tertiary carbocations are reversible under acidic conditions, such reactions must be kept as short as possible to prevent isomerization of the product. In this example, a larger excess of cresol was used to prevent its twofold alkylation. The reaction was catalyzed with 5% of iron trichloride. Here, a mixture of copper bromide and metallic iron catalyzed the benzylation of thiocresol with benzyl alcohol. Interestingly, the thiol was not alkylated. With anilines, however, alkylation at nitrogen is usually irreversible and can become significant during Friedel-Crafts type alkylations. In this example, with benzhydryl alcohol as electrophile, despite the use of only 10% of a Lewis acid, exclusive alkylation at carbon occurred. Also, in this example, only benzylation at the arene occurred, again with catalytic amounts of an acid. If toluene instead of hexafluoroisopropanol was used as solvent, however, aniline was benzylated at nitrogen. Hexafluoroisopropanol probably formed strong hydrogen bonds with the amino group and thus lowered its nucleophilicity. The trityl cation is easy to generate and therefore quite unreactive. However, aniline hydrochloride can be tritylated at carbon, as shown here. Now some examples of the alkylation of heteroarenes. Here, a reactive dication was required, and these can be difficult to generate. This was accomplished by heating the alcohol with polyphosphoric acid for 6 hours. Indoles are easy to alkylate at position 3. Here, the alcohol was first converted into an alkyl bromide, which cyclized to a thioranium salt. This cation then reacted with nucleophiles at the benzylic position. Indoles can also be alkylated with primary alcohols by transient oxidation of the latter to an aldehyde.
Alkoxides are good hydride donors and easier to oxidize than alcohols. Strong heating of ethylene glycol with barium hydroxide led to its dehydrogenation to hydroxyacetaldehyde. Condensation with indole, followed by reduction with hydride, gave a good yield of hydroxyethyl indole.
Alkylation of thiophene with tertiary carbocations is less regioselective than the alkylation of indole. In this example, a mixture of two regioisomers was formed. Still, alkylation of thiophene was fast, and no extensive cyclization or oligomerization of the electrophile occurred. Here, with a benzylic carbocation, furan was alkylated with high regio and stereoselectivity. The reaction was stopped after only 15 minutes to prevent isomerization of the product. Also, in this example, an acid-mediated benzylation proceeded with high stereoselectivity. The reaction was conducted in trifluoroacetic acid with half an equivalent of methane sulfonic acid. Here, an enantiomerically enriched benzylic alcohol alkylated indole with retention of configuration. The intermediate carbocation was therefore not planar, but configurationally stabilized by the silicon-carbon bond. The epoxides prepared from styrenes can react with electron-rich arenes twice and yield triaryl ethanes, as in this example. Here, again, acid catalysis was used. Let's check some alkylations with aldehydes and aldehyde acetals. Formaldehyde is reactive and tends to oligomerize. Here, the cyclic trimer of formaldehyde was heated with terephthalic acid in sulfuric acid. Despite the low reactivity of benzoic acids toward electrophiles, under optimized conditions, a good yield of the lactonized hydroxymethyl terephthalic acid was obtained. Alpha aminoacetals, like the starting material of this example, are difficult to hydrolyze because acids will first protonate the amino group, and hydrolysis then requires formation of a dication. Nevertheless, treatment with concentrated hydrochloric acid in this instance led to a clean cyclization and hydrolysis. Even 7-membered rings can be prepared this way. Here, to facilitate acetal hydrolysis, the secondary amine was first trifluoroacetylated. Reduction of the initially formed enamine with triethylsilane in trifluoroacetic acid then yielded the final product. Aminoalkylations of arenes with amines and aldehydes or ketones won't be discussed in this video because this is a huge subject by itself. This here is just one example of cyclization of an aryl acetamide with formaldehyde. Interestingly, even an unreactive nitroarene could be alkylated this way. When arenes are alkylated with aldehydes or ketones, benzylic alcohols are formed. With acids, these alcohols form carbocations, which can be reduced to alkanes with triethylsilene, cyanoborohydride, catalytic hydrogenation, and sometimes even with alcohols. Here, 1,3-propane diol was used as reducing agent, and it is assumed that this reduction proceeded by an intramolecular hydride transfer. Phenols are easy to alkylate with aldehydes or acetals, but the resulting products are unstable and readily oligomerize. Here, phthalimide was first reduced to a benzpyrrolidone and then added to glyoxylic acid. The hemiaminal alkylated 4-fluorophenol ortho to the hydroxy group. The reaction of aldehydes with anilines is complex and can yield a multitude of products, depending on the conditions. These have been studied carefully, though, and before testing anything, the literature should be double-checked. Here, nitroaniline was condensed with paraformaldehyde in hydrochloric acid. A symmetric diaryl methane was formed in high yield. The first product of the condensation of formaldehyde with aniline is a diaminomethane. Upon heating with acidic catalysts, this compound can isomerize to 4-aminomethylanilines and, upon stronger heating, to symmetric diaryl methanes. These are valuable monomers for polyurethanes and other polymers. With 2 equivalents of formaldehyde, aniline can also be converted into the polycyclic compound shown here.
a so-called Troger's base. Usually, when aldehydes are mixed with amines, acids, and some hydride donor, reductive alkylation of the amine occurs. With dimethoxyaniline, however, exclusive alkylation at carbon occurred.
Similarly, thiophenol can be alkylated at carbon, for instance with benzaldehydes and catalytic Lewis acids. Aldehyde acetals, like protected carbohydrates, can alkylate electron-rich heteroarenes. Here, with a large excess of furan and a slight excess of boron trifluoride etherate, a multifunctional carbohydrate derivative was prepared. I'll show you now some examples of the reaction of metylated arenes with aldehydes and ketones.
Polyhalogenated benzenes are acidic and can be deprotonated by strong bases, either partially or stoichiometrically. Here, a dichlorobenzamide was lithiated with sec-butyl lithium and then hydroxyalkylated with benzaldehyde. The reaction had to be conducted at low temperature to prevent the formation of an arine by elimination of lithium chloride. Stoichiometric metylation can sometimes be avoided, though. Here, a mixture of chlorothiophenone, benzophenone, and lithium tert butoxide was heated in DMF to 105 degrees Celsius for 20 hours, and a fair yield of a tertiary benzylic alcohol resulted. Similar reactions can also succeed with 1,3-dichlorobenzene and related polyhalobenzenes. Diaryl ketones, like benzophenone or fluranone, are much less reactive than aldehydes, but can be converted into diaryl methanes under forcing conditions. Here, toluidine was condensed with fluranone to a symmetric diaryl methane, suitable as monomer for the manufacture of polymers. More reactive are pyruvates. In this example, depending on the conditions, either a tertiary alcohol or a diaryl methane could be prepared. Sometimes chemistry surprises us. When tetralone was treated with an excess of benzene and aluminum chloride, tetralone reacted at the para position of the keto group. Moreover, oligomers of benzene were also formed. Which brings us to potential side reactions. Alkylarenes with benzylic hydrogen are potential hydride donors and are often easy to oxidize, also by carbocations or acids. Here, the dipararose-aniline was prepared from formaldehyde, hydrochloric acid, and air as oxidant. Just as aldehydes and ketones can react with arenes to diaryl methanes, carboxylic acids should yield triaryl methanes when heated with an electron-rich arene and some acid. This reaction is difficult to achieve, though, and it usually stops at the aryl ketone or diaryl ethylene stage, as in this example. Then, because alkylation enhances the nucleophilic reactivity of an arene, Friedel-Crafts alkylations will often occur more than once unless a large excess of arene is used. Here, phenol was methylated 6 times by strong heating with methanol. Treating phenols with bases and alkyl halides usually yields aryl ethers only. With olefins and alcohols, however, alkylation at carbon is possible. Still, even with alcohols, alkylation at oxygen can occur. In this example, heating phenol with methanol and catalytic potassium benzoate gave anisole as the main product. Also, anilines are sometimes alkylated at nitrogen by alcohols. In the example shown here, a mixture of products resulted when aniline was heated with cyclohexanol and an acidic clay in heptane. With aldehydes and ketones, imines are formed that can rearrange to alkyl arenes upon heating with an acid. But if reducing agents are present, imines will be reduced to amines. The reductive alkylation of amines at nitrogen with aldehydes or ketones is an important strategy to prepare amines. The reaction of electron-rich arenes with aldehydes or ketones can yield benzylic alcohols or diaryl methanes. At high concentration, oligomerization of the product can become an issue, as in this example. Here, when the cyclization was conducted at a low concentration, a high yield of tertiary alcohols was isolated. At a 10 times higher concentration, however, a product mixture resulted.
This is a problem for large-scale industrial preparations because the concentration at which the reaction is run has a strong impact on the production costs. The higher the concentration, the less expensive the product. Here are some more examples that you can also find in the description of this video. Under the Posts tab of my channel, there is a copy of the slides. The next video of this playlist is about the alkylation of unsubstituted arenes with radicals and carbon nucleophiles, for instance, polar organometallics. This strategy is best suited for preparing electron-deficient alkylarenes. See you there.